So, hello everybody. Most of you know me, Philipp Tomsich from VRULL. I'm also with the Software HC, and one of my areas of expertise and one of the areas my company and my group is working in is the compiler optimization for RISC-V. Mainly with focus on the big benchmarks, including the SPEC suite. And today I'm going to give a quick overview, and I was asked to give more of a why than a how presentation of what we're doing in the compiler environment on RISC-V and how we're trying to help with the evolution of the ISA, as well as to improve the overall code quality by having a slightly more data-driven approach to all of this. So maybe let's revisit the facts of life. So number one, life is complicated. That's probably nowhere more true than with compilers and workloads, given that what you're doing for one workload might not trigger on another. An optimization that goes into one area might not be generally applicable, and at the same time we need to get all the expected workloads up in terms of performance and try to drive their performance. So one of the problems that we've seen with RISC-V generally and over the last couple of years is that a lot of the performance effort has really been completely focused on embedded. Focused on embedded here means small benchmarks. Small benchmarks inherently behave differently from large benchmarks. So if we're looking at Drystone, if we're looking at MBC Coremark, on the one hand, we understand them very well. There's a couple of critical loops, a couple of critical operations. They are typically just cache resident, and we can optimize for them quite nicely. I mean, notwithstanding surprises and even ISA levels of surprises that we can talk about later. But that does not really necessarily reflect on what's going to happen when we have larger workloads. And when I'm saying larger workloads, we're trying to move into data centers. We're trying to move onto the desktop. So RISC-V today is trying to escape that small workload, small benchmark mindset. And I'm seeing more and more SPEC results being published. Those SPEC 2006, well, you can't publish those anymore, given that the benchmark has been retired, and people looking at SPEC 2017 performance. One of the benefits of that is that we are testing the whole systems, that we're testing cache behavior, loop behavior, ordering your memory accesses, doing prefetching, modular scheduling becomes much more important, and also corners of the instruction set architecture that might not be exercised that much otherwise will get exercised. So very clearly our focus, and the focus for this talk, is SPEC 2017. And one of the questions is, how do we make sure that we put our resources, given that RISC-V still has very limited resources, where it matters most? So one of the things that we have noticed over the last couple of years is that small benchmarks do have interesting side effects in terms of motivations. It's very easy to just get the number right. So that's what we call benchmark abuse. People might bypass the run rules and simply use optimizations they're not allowed to use to break the benchmark, or they might even go in and change the source code. So I've seen benchmark numbers and white papers on Coremark where the overflow semantics of area indices were changed. Clearly, that gets your number up. That might be great on a marketing deck, but it's not going to benefit the ecosystem in general. On the other hand, SPEC 2017 makes that much harder. I must say, yes, guilty as charged. We have even done very focused things on SPEC over the years that were not generally applicable if time was pressing and we just needed to get the result out before it could be cleaned up and made generally applicable and pushed upstream. But generally speaking, because it is a big benchmark, it is hard to cheat on it. It's not, you're going in, you're changing that one thing, and I see somebody in the audience who spent years on SPEC benchmarks nodding because he exactly knows what it is. The problem with SPEC is exactly that. It's very hard to make a major advance. On the other hand, if you make advances, whether they're small or big, they will usually be generally applicable and give you a benefit across the board, not just for that one workload, not just for that one benchmark weight. So to very quickly review what SPEC 2017 is, since some of you might not know it, it is exercising integer workloads, floating point workloads. There are some vectorizable ones. I'll get back to that later, given that vectors is now coming into play on RISC-V. And it has a built-in validation. I've seen it being used as a design validation tool, just as well as a benchmark. It's going to be long-running, shake out even issues that you might have with your instruction fetch. And it has become the industry standard to actually compare real Linux systems, Linux servers, Linux desktops. I know there's a drawback when it comes to RISC-V community, and we haven't had as much adoption of it as we could have, and that is its license agreement. So it is a closed source license. You need to get your license in order to work with it. You can't share the source code with others you might be collaborating. It is not a prohibitively priced license, but in an ecosystem where everybody is focused on open source and open collaboration, this may be a roadblock. Still, it is the best tool that we have today for benchmarking, so we should really consider using it. All of this plays into the competitive landscape a bit as well. So ARM has had going on a focused effort to get their SPEC scores up, to fix issues with the auto-vectorization, and do whatever is needed. There's plenty of public evidence to that. So Kirill Chakov gave a talk at the 2019 Cauldron where he was summarizing vectorizer issues. They announced auto-vectorization improvements for X264 in a public blog. There's recently been going on an effort to implement patches and improvements on LLVM for SPEC. That is being upstreamed through one of the subcontractors. And of course, Intel and AMD have put considerable effort in optimizing for SPEC. All of that is immediately apparent if you go to the SPEC website. Just look up the scores and you see, especially historically, you see how Intel and AMD were going for the lead. IBM was playing the SPEC game nicely. And then suddenly ARM started catching up. Now, when RISC-V really has hardware and we're going out with server-level products, what we're going to see is that the same catch-up that ARM has played is going to become a focus for our ecosystem. So at that point, it's better to get started early than to get started late. For us, as I mentioned before, life is going to be even more interesting than for some others because we've just ratified vectors. We have vectorizable workloads, and Intel, AMD, ARM, playing a game of catch-up to see who is the best and also who gets the best ISA extension and ISA instructions and compiler support into it for these benchmarks. For us in RISC-V, we're just starting there now. We're having the vector extension. We don't have auto-vectorization at this point, and this is going to be one of the main focus areas we need to go into. At the same time, nobody has really evaluated our vector extension for what's going to happen once we have the compiler. So how auto-vectorizable are we for these instruction sets? And do we need additional instructions? Should things have been defined differently? There's an effort going on to optimize for the intrinsics and string functions. This is a topic coming out of the bitmanip, so there's very efficient ways to do a string length, for example, if you have instructions from that. And of course, we need to build up some infrastructure to use our zeroization because there is one benchmark in SPEC that actually benefits a lot from being able to zeroize 64 bytes of data. So basically a memset 0 that can be optimized into a single instruction. And that, by the way, is one of the drivers why ARM had that data cache zeroization instruction. So As RISC-V, we have the problem that there is loads of experience with this. We all know what needs to be done, but we're still at the stage where there's a risk that we might repeat the mistakes from the past. Because, again, everybody has done it before. We now have the instruction sets out, or the instruction extensions out, but the compiler effort is still behind. In order to really advance the compiler state, we've been working with a methodology that is quite iterative. So we've built an analysis workflow, and I know everybody's going QEMO. That's just a functional model. But there is a reason for that. So we're working with a workflow that uses a fast emulation, in part due to the fact that the instructions we're targeting aren't even available in hardware yet. And plugging that into a quick cycle with GCC and LLVM. So the goal there is to catch as many issues automatically and also assess the awareness or the maturity of the compiler in terms of compiling for those extensions as fast as possible. So run the workload, collect your data, get some instruction histogram information, look at the hot blocks, define some search scripts or analysis scripts that are working on those hot blocks and the traces in the disassembly to identify hotspots, go back, improve the compiler, rinse and repeat. One of the problems there is that a lot of the analysis is still happening by hand. So yes, counting the histograms is easy. Counting instruction histograms, knowing if you're having 10%, 15% bit manip, if this is cutting down on the addressing side. But if you're trying to see if there are missed opportunities, that means defining actual search scripts that are going into text, into disassembly, and working with that. And at the same time, we're limited by perf, of course. So the only metric we have is dynamic instructions, which obviously doesn't really relate to real-world throughput. So even if we have the CBO0 example before, it depends on the specific microarchitecture, if that's going to be 1 cycle, 5 cycles, or actually it's just unrolled into a number of stored primitives. We can't do anything about it, again. We don't have the hardware. So in our model, we're defining the ISO specification. It goes to freeze, it goes to ratify, people start building hardware. FPGAs might be available earlier, RTL models might be available earlier, but actual hardware with large memories attached. And that can be easily scaled up, so run a couple of them. That's something we can only do in simulation at this point. And QEMU is the fastest emulator. So before I jump into some raw data that we collected, I'd just like to go back into how does this methodology actually help? Are we able to bring in tangible results for the community? And if we would scale this up, could we help mature both the ISA development process as well as the compiler development process more quickly? And there's actually, we've been doing that for less than a year, and there have been a number of greatly promising results. So on the one hand, the methodology was developed for assessing bit manip. So ZBA BCS, assessing it with actual large workloads. And what we did on that front is we gathered histograms. We looked at the maturity. We saw that certain instruction patterns are more likely. There were even overlap in instruction patterns. And by addressing that, by doing the analysis, this gave us an opening to make the specification better, so that information was provided to the actual task group, and then they made a selection on instructions that they wanted to do first. Not surprising, the biggest win really comes from the addressing ones. Profile-driven optimization in GCC gets a big workout with this. So earlier this year, early in the development cycle for 12, and just in time for the release of 11, we still got a major issue with profile optimization, profile-guided optimization on GCC, identified and fixed. It doesn't have anything to do with the instruction set. It was just a RISC-specific bug at this point that could be found by giving it a continuous workout. Because this didn't show up with small workloads. This didn't even show up with most of the SPEC workloads, but one big workload triggered it. Same with the branch window. So depending on what you build, depending on how you build it, your function sizes might get big. If we are heading into this high performance territory, things get weird. I mean, they get really weird. Loads of inlining, reordering, and if you're having the right workload, and SPEC has one workload that is very right for that, you might end up with functions that are tens of megabytes in size. That makes the internal branching suddenly very interesting. And again, bug identified, bug fixed, patches posted. We can now deal with larger functions. And finally, ZBO0. This is one of those instructions where you don't really know what's going to happen. How applicable is it, especially with the flexibility in what our CBO length is. This was one area that we could very quickly evaluate and track back to that one workload in GCC, which by the way is in SPEC, which by the way is the GCC workload in order to evaluate. But let's just, given that time is running, let's just dive into some of the results. So one of the questions that we were asked very early was, how useful are the individual instructions or the individual subcategories that go into bitmanip? What this graph shows, and I know you can't read the labels, is how each of the components, so we're having integer, we're having floating point running in SPEC. So those are the two bars on the left, the comparison. And then each one of the components run as rate or speed workload, how they're hitting A, B, and C. So that's the categories, the colors on top. What is very quickly visible here is that the addressing ones are giving us the highest bang for the buck. After that, it's the basic bit manipulation, and finally the bit setting ones, which come into play on some of the benchmarks. And to anybody who knows the benchmarks well, it's not surprising where they're coming in. So this is also a bit of a confirmation that the compiler is doing what it's supposed to do. So Perlbench, for example, is setting bits a lot on data structures, marking objects as garbage on its heap and similar. If we didn't have any of the bit setting instructions there, we'd have known that something was going wrong. A bigger question yet during the standardization of bitmanip though was we had two types of zero extensions, prefix and postfix. And one of the big questions there was, do we really need both? So they're taking up opcode space, actually making the decision what the compiler should do harder. And having postfix zero extension also had a very interesting impact on our design philosophy. So we always had a sign extended 32-bit register. If you're suddenly doing that, you're having an operation that performs a 32-bit operation and leaves an zero extended 32 operation as a 64-bit value in an object. So our entire type system was affected. So what to do? Easiest on that front, you just remove the support for either one and then look at how the frequency of hitting them changes. And one of the things that became very, very quickly apparent, and this is comparing no bit manipulation, once with postfix and prefix, and once without postfix. What became apparent almost immediately is there were barely any good uses. So if you're in the 0.0 something percentage in terms of difference, adding that additional instruction probably isn't worth it. So what we learned from that basically is that if we want to drive ISA extension development in a manner that it benefits the software most, and let's not forget we have to be very careful about the limited resources we have. So every opcode in the 32-bit space that we use is used up. We can't recover that. What we need to do is we need to get early results in from the toolchain co-development. Apparently that means every time an extension comes out, somebody needs to work on the tool chains so that they can gather data. But beyond confirming that, and it's been suspected for a while anyway that we need to do that early, and that needs to be part of our process, because it even went into our definition of done. Besides that, we've also been seeing that this data like this, because this is just a snapshot out of many gigabytes, and analysis run over many gigabytes, that data like that and analysis like that can actually drive decision. So a lot of our members are semiconductor companies. And there are trade-offs, decisions every day in designing the silicon. For example, what fusion patterns would benefit us. That is something that can be easily done if you generate the traces, if you do a query, and if you have an idea what you're looking for. Plus, you can prioritize it top-down from your hot blocks. So just look at what instructions are most frequently executed, where you're spending your time, so to say, even though your time base is dynamically executed instructions and not real retired instructions in time. You can still identify potential fusion patterns. You can then query that, and that is quite helpful in evolving your microarchitecture if you're fusion capable. It can affect other, and I can't discuss that in much detail, other choices in microarchitectures, because you suddenly see what is your typical operand size if you're having immediates in there. So what sizes or what values for immediates, for shifts, for rotates are going to be common. And finally, and most importantly on the actual hardware side, we're gaining valuable data for the development of extensions. So probably most valuable is we know what not to do. So if we're putting something in, if we're implementing it, and we're seeing no real gain from it, no real applicability, an enormous cost to implement it in the compiler, and then very few cases triggering. And that's a trade-off also, again, where we need to take the opcode consumption into account. We probably don't want to do it. On the other hand, we can identify cases where we want to add instructions by looking at the hot blocks. And finally, and last but not least, the prioritization of compiler work. So again, it's a limited group. We have very limited resources. We need to go through that. Since I've already received the time check, I'll just quickly skip over the ZBO0 data. Much more interesting, because we have some more interesting cases to look at and actual findings. So this is, for example, from a sequence in one of the SPEC benchmarks that shows how we are limited today by the definition of our minimum instruction combined with a compiler weakness. So in this case, we are seeing a number of 0 extensions before minimum, because what we're trying to do is take a 32-bit minimum, unsigned 32-bit minimum. However, we only have a 64-bit minimum instruction. If the compiler doesn't know that it's dealing with 32-bit values that are already 0 extended in its registers, it can't use that instruction. It's going to create additional code, basically prologue and epilogue code in every loop in order to convert the values so it can use the minimum instruction. I'm highlighting this example because it is a hot block that contributes over 5% of dynamic instructions to one of the SPEC benchmarks. So in this case, if we hand optimize that, if we write the assembly by hand, if we know that this is a 32-bit unsigned value, this drops by about half, I think, 35% it says. So that's a 1.58% reduction in dynamic instruction count. And that's the sort of data that a continuous improvement cycle and the continuous cycle is going to yield, and where we as members also need to figure out how to share that data. Because it's fine if one organization doesn't have the resources to actually address the issue at any time, but they do the analysis, they find the issue, they document it, and we can put it up into the community so that everybody else is aware, and whoever has the resources and the leaning to address that can go over that. And before Jeff kicks me out of the room, just one final slide here. One thing we've seen, and a lot of people know that I've been pushing both for performance modeling tools as well as performance analysis tools, and getting a concerted effort to drive that forward within RISC-V. One thing we've seen is that our understanding of what's going on is still quite limited, and we're still biased. So QEMU is not an optimal tool. Dynamic instructions is not representative of real world. And we do have access to the RTL emulation of one of our partners. So we know what's going on one out-of-order superscalar chip. But again, that is not representative. And what we as an ecosystem, and all that I've shown, is saying, well, we have a methodology. We have something that might help us, but the data is still flawed. And what we will need next is actual cycle-accurate simulation and some level of sharing that people make their models available, and that we can actually test this cycle-accurate on in and out of order. Thanks.
Please give Philipp a round of applause. Yes. Philipp, the one question I will ask, since we're out of time, is how do people get in touch with you if they want to help, if they want more information, if they had a great question we just didn't get to?
Okay, my contact is pretty much available everywhere on RISC-V, given that I'm the software HC chair. Worst case, please come and join the software HC meeting or the toolchains and runtime meeting, where people are actually discussing these things and where we need helping hands at all the times.
Excellent. Thank you very much. Give him one more round of applause.